Welcome to Edwards Vacuum Laboratory Talk Podcast. I'm Dan Rutherford, and I've worked in multiple roles during my 24 years at Edwards, and I'm currently the Market Sector Manager for Analytical OEMs.
And I'm David Steele. I'm the Market Sector Manager for R&D, and I've been involved in vacuum technology for about 35 years, just over 25 years of that time at Edwards.
Hi, and I'm Todd and I've held various positions within Gamma Vacuum and Edwards Vacuum since 2009, primarily supporting UHV and XHV customers and sales channels in North America.
For our first few podcasts, we've decided to go back to basics, back to the very basics, in fact.
Way back. Today, we're going to spend some time talking about the basic principles of the technical uses of vacuum, what vacuum is, how it's measured, and how it can be displayed in different ways. We're going to talk about some of the differences between measuring pressure in absolute and relative terms, and talk a little more about some of the various units of measurement that are used to express very low pressures.
Today in vacuum science and technology, vacuum is used to support a wide variety of research and manufacturing. We're going to chat a little bit about the fundamentals today to try to help someone just entering into the world of vacuum technology.
Yes, it's used everywhere in modern manufacturing, science, and research and development. Even though that vacuum technology plays such a huge part in our modern world, it's not widely taught in schools and colleges. And without a baseline of shared understanding of how we talk about it, well, like many other topics, things can get confusing.
Yeah, it is pretty surprising. It's not really covered much in school or even at all, right? Engineering courses at the degree level, again, same thing, not much talk about it at all. Good news is the American Vacuum Society does offer some basic classes, and there's a few other colleges around, and I know a junior college here in Minnesota. But otherwise, it tends to be kind of learned as you go along.
A sort of osmosis.
Yeah, exactly. But unfortunately, along with that, some of the myths and legends, get developed. Sometimes some internal knowledge within an industry or within a company itself, and there's different misunderstandings that formulate and just kind of get passed along through generations.
So let's start with a basic question. What is vacuum?
Ooh, good question.
Well, the most straightforward definition would simply be any pressure that's less than atmospheric pressure. And pressure itself can be defined as the force applied to an object, whatever that object is. We usually think about vacuum chambers in vacuum technology. It's the force applied to an object by something pushing against it, like a compressed gas.
So then why doesn't vacuum always get expressed as a negative pressure then?
Well, we're used to looking at a pressure gauge, say, when checking the tire pressure in a car or a bicycle. And if the gauge shows a pressure of 0, then the tire's flat.
Correct. That's right. And that's why we properly refer to this as gauge pressure, as it is the pressure indicated relative to atmospheric pressure on a gauge that starts at 0 for atmospheric pressure. Any pressure higher than this is positive, and anything less than this is negative. But again, only when we're talking about gauge pressure, where you're comparing to atmospheric pressure. So if you're dealing with gauge pressure, then yes, you do have negative pressure reading relative to atmospheric pressure.
Yes, that's right. And we do have to remember that in actual fact, atmospheric pressure is actually about 1,000 millibar or 14.6 psi or 29.9 inches of mercury or 760 torr. We're going to talk about pressure units later on. Absolute pressure, where a perfect vacuum environment exists, that's one with absolutely no gas molecules in it at all, that would have a pressure of 0.
0. So a perfect vacuum is 0, and that's on an absolute scale, and it can't be negative. It's an absolute level, but it's really just theoretical.
That's right.
That's right, yeah.
But in reality, there are always some gas molecules, even out in the vacuum of outer space. So absolute vacuum measurements are always a positive number. Although in many cases in high vacuum, that is a very, very small number. This is why vacuum technologists tend to use logarithmic scales when measuring pressure.
So things like turbo pumps and ion pumps can get to some really low pressures, somewhere in the neighborhood of less than 1/1,000,000th of atmospheric pressure.
Yes, and a vanishing tiny number. And that's, again, why we use the logarithmic minus number scale to make sense of these tiny, tiny numbers. But we'll talk about that topic a little bit later on as well.
So to be completely correct, we should really refer to vacuum as a partial vacuum because you can never really get to perfect vacuum.
Yes, that is true. But as long as we all understand that that's what we really mean, we don't have to say partial vacuum all the time. I think it's okay to say vacuum.
Makes sense. But is something like negative pressure, is that even useful?
Oh, well, in some situations it is. For example, if the pressure differential between the vacuum environment and the atmospheric air is what is important to what you are doing, then it is.
Oh, so like if you're using a vacuum puck to pick up something like in a production process, for example.
Exactly. Vacuum handling or vacuum assisted filtration would be perfect examples.
So in those examples, the amount of negative pressure, gauge pressure, can only be as much as the difference between actual atmospheric pressure and whatever the vacuum pump that's being used is technically capable of reaching on an absolute scale.
Yes, and that's why there's an extra challenge when operating this sort of equipment at high altitudes. So, Denver, the mile high city, typically has an atmospheric pressure that's at about 80% of what you experience at sea level. So, you can never get a vacuum gauge pressure better than that.
Yes, that is a common request. Can I get a pump that will consistently give better than 30 inches of mercury? And the answer is no, because that would be less than an absolute zero pressure. The only way to achieve that level of pressure differential between the high pressure and the low pressure sides would be to increase the pressure on the outside. And that's something that products like autoclave ovens do.
I think it's a key concept to grasp that it's not immediately obvious, is that we need, even though we are used to a vacuum cleaner sucking up dirt, a displacement vacuum pump like a scroll, RV, or diaphragm pump doesn't actually suck the gas out of a system. It creates a low pressure inside of it by compressing gas to a higher pressure so the molecules are actually pushed towards it.
That really helps us to explain, how it's the higher pressure that's pushing, and I'm using the term sort of figuratively, not literally, rather than a vacuum pump that is pulling the gas in. We'll be talking about that much more in other podcasts when we talk about high and ultra high vacuum.
So would it be fair to say that inside a fixed vacuum chamber, unless the difference between the inside and the outside is important, the relative pressure is largely irrelevant? Once inside a fixed leak-free vacuum chamber, the pressure going on the outside won't really directly influence anything that's happening inside of that vacuum vessel.
That's right.
Yep, I agree. Yep.
Hmm. So the summary would be here that in vacuum technology, we generate low pressure by compressing a gas or vapor to a higher pressure or capturing or trapping it, and the vacuum pressure simply gets smaller and smaller, approaching zero. Hmm.
So after talking about all of this, it's worth us chatting a bit more about the units that we use for vacuum measurement because they can cause quite a bit of confusion. And vacuum measurement is one of my favorite things after all.
Oh my,
Sure.
yes, yes. There's so many different units that can be used. But why isn't there just one standard unit that's used by everybody around the world, regardless of what you're doing and what you're working on?
Well, a big part of that comes down to metric or international standard units versus imperial or other scales, along with some local and even industrial preferences that have been developed.
Yeah, yeah. Kind of well, that's the way we've always done it kind of thing, huh?
Hmm.
Yep. There is an international standard. The international standards or SI units for pressure is the Pascal, who, little history lesson, named after the 17th century polymath Blaise Pascal. And it's defined as 1 Newton of force per square meter. It's commonly used in Japan and Korea. It's probably the most common vacuum unit of choice there. And it's also commonly used everywhere in academia, but again, not exclusively.
And the bar and millibar are commonly used. Here, 1,000 millibars equals 1 bar, which is 1 atmospheric pressure.
Yeah. That's why sometimes you see strange units like a hectopascal, in different industries or in some companies. And that's really just the same as a millibar, but without using the scientific units, albeit not in a widely used multiplier like milli or micro. Hecto is a little strange. It doesn't flow as easy.
It's kind of like you're still using millibar, which lots of folks are used to, but you're expressing it in an SI unit instead.
Yeah. All right.
Exactly. And when talking about weather and air pressure, it's pretty common to hear millibars and not hectopascals. It's just what folks are used to.
Right.
I'd say in the US, the millibar and the torr are the units that are probably most widely used in the high vacuum world in both industry and the applied sciences.
So there's got to be a pretty good backstory surrounding some of these different units and where they all came from and originated from, right?
Yeah, so because pressure, a unit of force on a given area, was measured in the early days or the before the days of vacuum technology with different types of gauges, vacuum technology simply adapted those types of gauges and they modified them and used them. So mercury manometers, for example, were probably the first type of low pressure gauge or vacuum gauge, and they measure the height in millimeters of a column of mercury. And that's where the name torr comes from. It's an homage to the physicist Evangelista Torricelli, who first came up with the barometer. So 1 torr equals 1 millimeter of mercury. And interesting, another factoid from me, both Torricelli and Pascal, who were contemporaries, although a few years apart, they both died very young at 39 years old.
What a shame. What a shame. So that's why the units of torr and Pascal are mostly capitalized because they're really named after real people.
Yeah, and because standard atmospheric pressure at sea level is 760 millimeters of mercury or 760 torr, 1 torr is equal to 1 7/600. Boy, I can't say that very well, can I?
A big
One
number.
760th of atmospheric pressure. So you can see how all of this gets confusing fast.
For sure, for sure. But I've also read some stuff and some interesting articles about using inches of water. Dave, you mentioned inches of mercury or millimeters of mercury, but how about inches of water?
So that's using the same principle as a mercury manometer, but using a column of water instead. How much of that column can be supported by the atmospheric air and the pump?
So atmospheric pressure will support a column of water about 400 inches tall. It's not used much in high vacuum technology, but it is used for things like gas extraction. Again, one of those industrial things. But that's also why you can't suck up water from a well that's more than 33 feet underground. Once you get below that, the low pressure equals the vapor pressure of the water at ambient temperature conditions, and the water starts to boil.
I'd also have another challenge to it. Could you imagine reading something that's 400 inches tall? You'd have to have people on ladders to get your actual measurement of where you're doing your study, right?
Yeah.
So there's another term that I've heard, hard vacuum. What actually is hard vacuum?
Well, that's one of those sort of fuzzy terms that isn't really well defined. I tend to agree with the definition that it's something better than a 99.9% perfect vacuum. So something in the single millibar or torr range, 1 or 2 millibar or 1 or 2 torr. But there's also folks that say it's a pressure that's better than 10 to the minus 3 torr or better than a millitorr, for example.
Yeah, but sometimes folks just use it to mean this is the lowest my pump can reach without leaks. So it is a very fuzzy definition.
Sure. And another unit that we don't talk about as much, but we can't forget about the good old pounds per square inch that gets used sometimes as well, right?
And that's one that's very commonly seen on dial gauges that measure both positive gauge pressure and negative gauge pressure, meaning lower than atmospheric pressure. It's fairly common to see negative pressure per pounds per square inch used in vacuum applications like vacuum chucking or conveying, when the difference between atmospheric pressure and whatever is being held or moved is the important factor.
So for most of the rest of these podcasts, we will try to be consistent. We're going to try to stick to talking about millibars when talking about pressure or vacuum pressure, because it's probably the most commonly used unit used when dealing with small sized vacuum pumps in a scientific or laboratory type environment, in North America, at least where the three of us are all sitting.
Sure, sure. And the other one that is used is torr, and getting to torr from millibar is pretty easy. You just multiply it by 0.76. One thing that does make it confusing, though, is when you're first starting out in vacuum technology, and in particular when you're moving into high vacuum, is the use of logarithmic scales.
So log scales are commonly used in the expression of low pressure vacuum, because on an absolute scale, you can never actually get to zero. You just get progressively closer and closer to it.
So that would make sense. So the log scales are really helpful when you're trying to show either really big or really small numbers, and you don't have to have all those zeros in front of your number.
Yeah, like Avogadro's number, 10 to the 23rd.
I remember that.
So if we round up atmospheric pressure, it's normally stated as 1,013 millibar. But if we round that up to say 1 bar is 1,000 millibar, that way it helps me with the mental arithmetic much easier. And we start off with a vacuum chamber filled with that gas. So it's a vacuum chamber at atmospheric pressure. 100% atmospheric pressure is 1,000 millibar. If we pump out 90% of the gas that's in that chamber using a vacuum pump, then the pressure in there would be a tenth that. It would be 100 millibar, a 90% perfect vacuum. And I'm making air quotes around a perfect vacuum. And if we keep pumping that, and we get down to 1% of atmospheric pressure, that would be 10 millibar or a 99% perfect vacuum. And you can see where I'm going with this. Every reduction of pressure by a factor of 10 you get, soon you just end up with too many zeros, 0.0000, after the decimal point, and it just gets hard for us to visualize what's going on.
That's right. So we can use a logarithmic scale for very low pressures. Pretty much anything below a millibar or a torr tends to use the logarithmic scale, as it helps make the progressively small numbers meaningful. Otherwise, really small pressure levels just look like you said, Dave, zeros, a bunch of zeros. But zero on a linear scale, where the distance between a graph, on a graph where a 0 to 1 is the same between 1 and 2, if we put it on paper, there wouldn't be much difference there. So it's easier to read this way.
Right. Now, on a logarithmic scale, each progressively smaller decade of pressure gets about the same amount of space, right, on the pressure scale. So, for example, 0.001 millibar could be written as 1 times 10 to the minus 3 millibar, or some people refer to it as 1e minus 3 millibar. And some people generically, and you have to watch the units here, but some people just call it the minus 3 scale vacuum.
And if you're working in torr, for example, there's also a commonly used scaling unit, the millitorr, which is 1,000th of a torr. So 1 times 10 to the minus 3 torr is a millitorr. So 10 millitorrs would be 0.01 torr, or 1 times 10 to the minus 2 torr. 100 millitorr is 0.1 torrs, and so on. It's a sort of a shortcut using 1/1000th of a torr.
So, with all of this said, the key thing to remember with all these different pressure units is when you're doing any calculations, make sure that you do the conversions correctly and making sure you're using the right multiples. Otherwise, your calculations are going to be miles off. And I'm sure we all remember this from our old math and science classes back in high school or college, when you do a perfect problem, but you tripped somewhere on a unit and you messed up the answer completely.
So a miscalculation here could mean the difference between, if you use it to make a decision to purchase a pump, you might need a pump that you could ordinarily lift up with one hand, but you end up calculating something that you'd need a crane to install instead. So there are real issues or challenges created when you make those mistakes.
Well, let's look at this. The three of us could rattle on about this for hours, so we better wrap this podcast up today, and so I think we should stop this here.
So in our next podcast, I think we're going to talk about a more practical topic, that of different types of vacuum metrology or vacuum gauging, how we measure low pressure in modern vacuum systems.
Tie into everything that we talked about today and put it into some practice a little bit. So remember, please continue to check back with us in the future, as we're hoping to release a couple of podcasts, a couple of months, maybe every week or two here. And if you'd like to reach out and give us any questions that you'd like to have us answer during a future podcast, please send us an email to podcast@edwardsvacuum.com. We'd love to hear from you, and we'll do our best to include your questions in future podcasts.
If you have any immediate need for information, you can always reach out to any of our technical support folks at Edwards Vacuum by emailing info@edwardsvacuum.com. Until the next time, this has been Dan, Todd, and Dave from Edwards Vacuum Laboratory Podcast.